Hello and welcome to this question, an applied redox balancing equation question using alkaline conditions, which can sometimes be a little trickier to deal with compared to acidic conditions. So firstly, let's look at the technique for alkaline conditions. It's very similar to the one for acidic conditions, except there's a couple of things to bear in mind. You start by assigning oxidation numbers to all elements, as you'd expect, and then you ignore the ones where oxidation number doesn't change. Then you can come back and balance the oxygen atoms both sides using hydroxide and water. So two hydroxides will balance one water because water has two hydrogens in it. You can go back to step 3 if the charges on the other side don't balance. So remember, hydroxide is negative, so it can be used to adjust for a deficit in negative charge on one side. And again, its only thing it affects is the water. So the water and the hydroxide can be played around with, leaving everything else alone. So once you've done that, you can check the oxidation number changes, see how many electrons were transferred, that is, gained or lost, and then you can multiply up, as normal, one or both sides to the electrons balanced, using the lowest common multiple principle. Finally, checking all the species and charges balance, you cancel your electrons, your waters, and your hydroxide as appropriate, before combining the two half equations to construct the overall redox equation that we want. So it's talking about manganese, several manganese compounds, and also chlorate 5 ions. And it gives you unbalanced oxidation and reduction half equations. First thing to do is to balance the equations and add the correct number of electrons to the correct sides of the two half equations. So firstly, like we said, assign oxidation numbers to everything, and then you can work out what's changing oxidation number and ignore everything else. So it's the manganese that is oxidized because its oxidation number goes up, and it's the chlorine that is reduced because the oxidation number goes down. So drawing a little arrow from one to the other, you can quickly work out what's been oxidized and reduced, just to remind yourself. So the next thing to do is to add in the electrons that are lost on the oxidation half equation and that are gained in the reduction half equation. So remember what we said. Use the hydroxide ions and water molecules to balance oxygens and charges, and the principle applied is one water on one side equals two hydroxides on the other. So a little bit of thinking about this and playing around gives us these. Now notice everything else has been left alone. You've still got 6 electrons on the reduction, you've still got 2 electrons on the oxidation. So now we need to multiply up as necessary one or both sides. So the lowest common multiple between 2 and 6 is 3. So in other words, you multiply up 3 times. So therefore, the top one gets multiplied 3 times, because remember, it started with 2 electrons being lost. Multiply that whole thing 3 times and you get this. The bottom one gets left alone, so the reduction has 6 electrons to start with, so don't do any multiplying down there, just keep it as it is. Now what you can do, remembering obviously that up here, just on the screen, there's a 3 in behind that little button there. So if you can bear with that name on that one, I'd appreciate it. So next thing to do is to cancel the electrons, the hydroxides and the waters. And then we can combine the two halves to construct the overall equation like this, which is what goes into the bottom part of the question. Okay, it's worth sourcing some examples like this. They're not that common, but they can be a little bit tricky when they turn up, possibly because there's actually not that many of them around. But it's worth looking for them and then trying out this technique on them until you're feeling a bit more confident about it. Right then, hopefully that gives you a little bit of a tip and some pointers to go and work on. Thanks for listening as always. Until next time, see you soon.